Calvo is a perfect guest now for taking a step towards the post-Anthropocene and also about telling us about the cognition and the consciousness of plants. He is internationally recognized for his pioneering research in the field of plant cognition, and at the University of Murcia, he directs the Minimal Intelligence Lab, and I love that title, where he investigates how plants learn, remember, and make decisions. And since we're at the decision making, you might have guessed that he is now challenges us a little bit about how he defines cognition and consciousness. And I'm really looking forward to Paco Calvo. Thank you.
Thank you. Okay, yeah, it's working? Yeah. Okay, great. Well, thanks for having me, Margarita, and organizers. It's great to be here. Just arrived yesterday evening, but I had enough time to see how beautiful and quiet and peaceful the place is. And I resonate throughout the day with a lot of the things you said, especially those in English. Unfortunately, I couldn't follow most of the things in the morning. My German is below 0. But no, now seriously, when she mentioned like 4E cognition, embodied, embedded, enacted, extended, I would add the 5E. We speak also of ecological, so it's like 5 E's, embodied, embedded, enacted, extended, and ecological. I'll say a few things about that. And in the case of Stefan, also I pretty much resonate with a few things he said, quite a lot actually. Especially this idea that we don't quite get, which is that we keep forgetting about it, right? Like, hey, intelligence is not something that you see. You just cannot see it. You can only infer it, right? The best thing you can do is to infer it out of the overt behavior. So I can check out your behavior, your behavioral repertoire. I can see how sophisticated it is. And out of that, I can infer that, hey, this guy is pretty smart. Depends on what you're doing. I might infer he's pretty dumb, right? I can also do what you mentioned, like, oh, maybe brain states, neural correlates of some intelligent behavior. There's some neural correlates, what flags, what lights up in your brain when you're performing a cognitive task, right? And that's kind of the same thing, and you can do with plants. So we can, and we do at the Minimal Intelligence Lab. I always joke with this idea like, hey, people say, why do you call them minimal intelligent? No, minimal intelligence is our intelligence in missing theirs, right? So I hope by the end of the talk, the message that Planta sapiens is not a metaphor. So I mean to say that plants are sapient, intelligent, sentient, in the very same way that I use those terms for humans, right? So Planta sapiens is not a literary experiment, it's not a metaphor. I do mean to say that they are intelligent in pretty much the same way, right? I know it's late, it's been a long day, but I have homework for you, okay? So, no, I mean it. So please concentrate now, because I'm gonna ask you to do something which is extremely difficult. So you will have to concentrate, okay? I'm gonna ask you to watch this clip, okay? To watch the clip that comes next. Please make the effort to simply watch the geometrical figures you're gonna see, triangles and circles. Just see them for what they are, geometric figures, okay? Okay, you'll see what I mean. Please, try hard. Just see them for what they are, geometric figures. Triangles, lines, that's it. Come on, you have to concentrate. It's hard. Now it gets mad. Okay, so yeah, really pissed off. But anyway, we were not supposed to be doing that, right? And I bet no one in the room was able to do it. We simply cannot. You just couldn't. If you raise your hand, hey, Paco, I could, you're lying. Nobody can, right? This is a psychological experiment from the 40s. And that's big news, because it means that we've got to be extra careful with the way we project our prejudices, our biases. What is it that we see, right? How theory-laden it is, right? So when we study plant intelligence, plant over behavior, and to infer plant intelligence, we need to check out. This is a BBC David Attenborough style, well, not a style, David Attenborough's documentary. I'm gonna lend my mic to Dave.
It waves its shoots agitatedly from side to side, as if feeling for the best way forward. And when a shoot settles on its course, it thrusts ahead relentlessly. The invading stem's backward-pointing spines give it the grip it needs to climb over almost anything that stands in its way.
You get the idea, right? So we need to clearly distinguish in between, hey, this agent is doing the things by themselves, for itself, as opposed to, it's doing nothing, I'm making it up. And we never know, because we need to infer it. Right? So how do I know that we are not making up stories about plant simply growing instead of behaving intentionally? Right? So that's what we try to discover, to find out in our lab. We do time-lapse photography, so we take pictures every minute, maybe, and assemble the footage and check what's going on there, what David Attenborough just did. But being extra careful not to anthropomorphize, as he was mentioning at the end of his talk, right? We also do electrophysiological recordings. We insert electrodes into the stem of the plant and record the electrochemical activity, electrosignaling throughout the flows of energy throughout the plant body, and study those non-neural correlates, assuming that you don't need to have neurons to be intelligent, right? So that's kind of the thing we do. So for example, say you have a climbing being. This is a vine climbing for a pole. We can study it kinematically. And by this, I mean trying to avoid anthropomorphizing the plant. So say I'm walking to the loo at night, my son left a toy truck in the middle of the corridor. He usually does. So I just, I try not to switch the lights on to go to the loo, not to wake anybody up. And then I just walk across the corridor and then, boom, the truck was there. You watch the video in the morning and you have to infer whether Paco bumped onto the truck or knew the truck was there. So out of the kinematics, velocities, accelerations, you can tell. So we can play the same game with plants. You can simply tell, hey, this plant is simply growing, and out of mere growth reaches its target by chance, by pure chance. Just it was a fluke, oh, lucky me. I bump onto the pole, here I am. Now I can go up there and do photosynthesis. Or am I intentionally trying to reach it? Is it goal-directed control behavior? right? So I would like to think that we have a way to tell that on a strictly neutral, non-anthropocentric terms, right? But being able to do that is not that easy, because if you are not wearing these glasses, you will wear some other glasses. But there is no way you can see the world without some bias or another. We simply swap one bias for another bias, but there is not the bias-free way of seeing the world, right? So we really need to make an effort, again, number 2, more concentration, to put ourselves in their shoes. So what is it that they care about? What is it that matters to them? And that's so important. It's really important because we need to make a strong, big effort. It's not that easy to forget about ourselves. So we need to forget about ourselves before we are able to put ourselves in their shoes. Because they don't care about our lives. Sorry, humans, I know you think you are proud of being Homo sapiens, but we are not that important to them. In fact, we are not important at all. So it's not their fault, it's not their business that you need to go shopping and cook dinner. They don't need to go shopping, that's why they are sessile. They do their own food through photosynthesis. They have their sugars, they don't need to go shopping. They might say, hey, you humans, how stupid you are, you need to go shopping, I don't. Instead of we saying, hey, plants cannot be smart, they are sessile, they are rooted, they don't need to move around. So what? They have different problems, they come up with different solutions, right? And yet, that's anything but easy. So that's my son's, a few years ago, we went on sabbatical to Edinburgh for me to write the book, and for my kids to enjoy life. And then I told my son, I said, hey, I tried not to bias him. I said, can you write, the idea of plant intelligence? At the time, the working title was Pflanzenkognition, the next revolution. And then I didn't say anything to him about what we do in the lab or anything at all, just to see what comes out of his naive mind, unbiased. And you see, that's what he came up with, obviously. He's at school, taking exams, sitting there boringly all morning long, listening to teachers. That's his life. Well, if plants are intelligent, there you go. That's what they have to be doing, right? So you just swap the glasses you wear, but it's very difficult to do it otherwise, right? So let's try to think of plants in themselves and for themselves, right? So I want you to focus on this plant, okay? Not this one. The one you're gonna see now growing right here. You will see a plant germinating that doesn't have chlorophyll, so it cannot do photosynthesis. It's a parasitic plant. So it needs to latch onto a host plant to suck up its sugars, right? So we need to put ourselves in their shoes. That's our tiny plant. Oh, yeah, there we go. I start growing. Do I just grow and lucky me if I find some host plant to suck up the sugars? Or do I need to think hard about it? Should I grow left or should I grow right? Right? There it goes. Yes, nice catch. Now drills into the vascular system and suck up the sugars. Right? So I want you to think about what's happening here right now. Remember, are plants simply growing, or are they intentionally reaching their goals? First thing is that for the plant to reach a target, if it's another fellow plant, plants are going to be absorbing red, the part of the light wave spectrum, and letting far red go by. So they will be absorbing blue and red. That's actually why you see them green, right? They reflect the green. So that means that, for example, the ratio, the proportion of red to far red light is going to be very meaningful. It's going to tell them the density of the canopy, how many neighbors there are around. If there is a guy around here, we're going to find a drop in the ratio because somebody's going to be absorbing red. If nobody's around, you're going to see the ratio going up, right? So depending on the ratio, you can tell whether I should be growing one way or another. But remember Margarita's 4E idea. Embodied, embedded, enacted, extended, right? So if remember when you were kids, did you play here this game, at least we do in Spain, like you are blindfolded and then you need to find the treasure. And then, right, your friends have to tell you cold, cold, or hot, hot, right? Okay, so I'm blindfolded and I don't move. so I'm staying like this. You cannot play the game. Because hot or cold only makes sense in the context of my actions. So I need to do like this for you to say cold, and then, oh, okay, this, cold, okay. I learned the lesson. I'm going to try this way. Hot, hot, you see? So I need to be behaving, acting in such a way that I close a perception-action loop that becomes meaningful in the context of my behavior. So I say, okay, now that way I get to navigate to my target by getting those clues out of the way I was behaving in the past, in the previous cycle, right? So that's what the plant is doing. Think of the plant as not simply circumnavigating. So it's not simply revolving around, growing in circles. The plant is not simply doing like this, and then eventually I will hit a target because I'm growing. No, it's actually sensing, monitoring how the ratio of red to far red light goes up or down depending on the direction. So they are playing the game being blindfolded. Hey, is it hot, hot, cold, cold, ratio up, ratio down? Oh, more guys here doing photosynthesis. I'd rather either go the other way if I want to find empty space, or go that way if I'm a parasitic plant and want to suck up the sugars. You see? But you are not only doing that. You have volatile organic compounds, so you can rely on chemical cues. You can rely on vibrations, mechanical stimulation. You know that some flowers can actually tell if this guy approaching me is a pollinator that pollinates me out of the vibrations, as opposed to some other insect that is not my pollinator, different pattern of vibration. And they will only increase the concentration of nectar if the vibration corresponds to my pollinator. So if the guy coming over here is my pollinator, I can tell out of the mechanosensorial stimulation, and I will increase the nectar concentration. If not, I won't bother. So all these signals have got to be integrated somehow. Light regime, chemical compounds, airborne, phytoacoustics, so many more cues. That's just 3, right? But you see, now we start to get an idea of, hey, the cuscuta, that parasitic plant, is not simply growing. It's definitely processing information. Well, we can see now plants as information processing systems. You see? They need to integrate all those cues in order to provide a response that is globally adaptive, like integrating all those cues, right? So that's the example of what's happening there, just mentioned. Okay, now think what we can do with this. A few years ago, we were funded to think of ways to inspire robotics and AI with plants, right? So that's, again, a great example in relation to your previous talk, because there is another way to improve navigation skills. So say you are a rover on Mars. Certainly, shit can happen and will happen, because we live in a world of, contingencies. There are regularities, but many things could go wrong as I move from point A to point B. So I need to navigate my surroundings and, avoid obstacles to reach my target. Okay? But from point A to point B, as I walk through on wheels as a rover, you might find a crack, you might punch a wheel, you might find a cliff, a sand dune, many things, right? And of course, you cannot code them all ahead of time. You cannot have them pre-programmed or keep adding lines of code. We can have different strategies, as he mentioned, but we can do something else as well. We can think of finding inspiration in other systems, biological systems that do get around in different ways. So if you see, sometimes it's better to simply change the question. Instead of saying, how do I get from point A to point B, and then we can have different discussions of which different architectures allowed you to do so, right? Reinforcement or not, whatever. Then you might say, hey, hold on a sec. Are we assuming that I need to leave point A before I reach point B? Because I'm a locomoting animal. Well, how about if I'm a growing plant? If I'm a growing plant, you saw from the cuscuta, to reach my target, I don't need to leave point A, because I grow from A to B. If I keep growing, I can shake you if I keep growing, and I will if you give me enough time, right? So that's important, because I don't leave point A. Cuscuta didn't leave point A. It grew all the way from germination spot onto the plant. And why this is important? Because sometimes you simply do away with your problems. You don't solve them, computationally speaking. You simply avoid them. So say I'm growing, I don't care about the crack. I don't care about the crack. I grow over the crack. There is a cliff or a little ridge. I don't care. I hang, like a hanging bridge. I keep growing. So you grow over your problems. Many times you can do that, right? In fact, going back to the idea, Margarita's idea of embodied, embedded, and acted. So think what's happening here, because we put too much emphasis on the idea that, hey, plants have no neurons. Who is at the wheel? Who is at the driving seat, right? Things like this. But hold on a sec. Check this is a root of rice at the top, and the bottom one is being knocked down gene. So it has a gene missing, and is unable to circumnutate. So it's unable to grow like this. So plants grow by differential elongation. So I grow this cell, this cell expands, so it's just like growing like this. It's oscillating, right? If you cannot oscillate, because you've been triggered, then you can only grow in a straight line, right? So the top one, you'll see, there is a pattern of behavior that emerges out of the interaction of a root tip that simply oscillates when confronting the surface it's growing onto, right? You see what I mean? Check the top one. That's exhibiting a pattern of exploration. It's exploring its surroundings by oscillating, but the bottom one that doesn't oscillate, because it's not oscillating, it grows in a straight line. Once it hits the surface, it just, right? You see? You couldn't find who is at the wheel guiding the exploratory behavior. It's the emergent result of a pattern of interaction in a distributed system. You see? Now, we can use this as a source of inspiration. Now, I told you about the Growbot, a growing robot, a robot that grows. Okay? You want to see it in action? Check this out. This is a robot that circumnutates, that oscillates. Okay? You'll find it on the left. And on the right, a robot that is stuck, that simply grows in a straight line. Okay? This is pneumatic actuation, by the way. We inflate it. Think of it as, you inflate the robot like a balloon. That's the way it grows, from the inside out. Think of a sock, like your socks, a pair of socks, like they are folded. When they unfold, they evert out, right? So it's growing from the inside out, right? So you'll see, if you circumnutate, you encounter obstacles, but you simply avoid them in an emergent manner. So there is no command center. There is no body deciding whether to turn left or right. It's the emergent outcome of an embodied system. And the one on the right is completely stuck. As soon as it finds an obstacle, it's stuck because it's not circumnutating. You see? But in both cases, the principle is the same. I'm simply, pneumatic actuation, being inflated and everting from the inside out, right? So this means that we can rely a lot of computational information processing cargo onto the periphery of the system. So we are obsessed with the neuronal, and maybe bodily constraints, material properties, morphological properties are way more important than we thought they were. So maybe sometimes they provide the clue. And of course, we thought plants were stupid, they had no head, who is doing the driving, and then, hey, you don't need it. You can do it in a distributed fashion. So materials allow you, when you are everting from the inside out, to do amazing things. Check what happens when you grow from the inside out. You don't care if you get stuck, because you get stuck from the outside wall, but because you keep growing from the inside out, you keep growing. Or you don't get stuck in the glue, or you don't get punched, or better said, you get punched, but if you have enough pneumatic pressure, you keep growing despite being punched, right? So that's all the things you can do if you're a growbot. Right? Oh, this is great. Look, for archaeological sites. You can go through a crack and then keep growing, because the crack is tiny, but then you keep growing because it's soft. We are calling about soft robotics, okay? So that's so important. Imagine, you go into an Egyptian pyramid, you don't need to remove the stones, and you go through a crack, and then you inflate, keep growing inside. If you have a camera at your tip, then you can tell things about the world and decide how to grow. If you have two chambers, you can add differential pneumatic pressure to the chambers. So if I inflate the upper chamber more than the lower one, it will go downwards. If I inflate the lower chamber more than the upper one, then it will grow upwards. So you can, with two chambers, you can make the robot turn and go one way or another. Right? Right? Okay, so that looks pretty dumb to many people. Oh, it's just a balloon growing. I mean, what's the fuss about it? But think that plants are, we've talked about distributed cognition, right? Distributed intelligence. You won't find the driver at the wheel we mentioned. And that means that they resemble, in a sense, patterns of collective intelligence or swarm intelligence. Like, if you think of a flock of birds, of a school of fish, well, that's not unlike what you find in a flock of roots, right? When you have all these individual root tips, remember that tip exploring, all these individual root tips that somehow need to orchestrate collectively the way, their decision making, the way they decide to grow one way or another, to find, a nutrient patch, not to compete your king, because they can tell king from not king. If you are my fellow, I might try not to outcompete you, or go for a, go do away with hydric stress, you name it. But all those problems get solved at the emergent level of the collectivity, right? So now there is a twist here. We can do something else, which is the following. We can think, as we move with LLMs, all the way from artificial intelligence, algorithmic, syntactic, prompt engineering way of engaging with ChatGPT like gadgets, to robots doing things in the real world, right? So now we are at the stage in which, hey, this is not about how you get to program your robot. This is about how you can have a robot first, okay? First, a robot that relies on sources of inspiration that are not related to locomotion. So think of the Growbot, okay? We have a Growbot. Then it is a Growbot made of soft materials. And that counts, because you can have a Growbot made of hard materials, 3D printing layers. But those will get stuck in the crack. You want it to be soft. And those material properties are the ones that allow it to go through the gap and then inflate at the other side, right? So it's got to be soft, it's got to be plant-inspired, you grow, you don't locomote, right? And then, what do we gain by moving into the real world of doing things out there? That you can see the result of your actions. So if I'm this robot, I just, boom, pa! I can see what happened and thereby make some adjustment as a result. So I can close the perception action loop by thinking, oh, that was the result of my actions, right? Okay? So imagine if you get to program, or to control, better said, to control a robot, a Growbot, a soft Growbot, okay? Are you with me? You get to control it with a generative AI. So a generative AI is going to give you something that is not to be thought as set in stone, is generative. So we can see the result of behavior, output behavior being governed by a generative AI. But this is collective. So imagine you have each root tip growing, or each Growbot growing, controlled by a generative AI, plus the added effect of having emergent features that have to do with how they collectively assemble. So you have all these robots that are navigating their surroundings, not simply governed by a controller, but by a controller that is generative, and on top of that, you are thinking of the global contribution or the global pattern that cannot be predictive or cannot be assembled ahead of time. Right? Okay? How much time we have left, Margarita? I'm lost. 7 minutes? Okay, good. So one of the problems, another problem we have usually with plants, intelligence, and comparisons with humans or artifacts is that we try to think of plants as having their sensory organs located somewhere. So you could say, hey, where do they have their ears? Where do they have their nose, their eyes? So how do they see the world? How is this climbing being seeing the pole, right? That's because we are, again, animal-centric. The same as with locomotion. We think in terms of locomotion, or we think in terms of where do they have their ears. So their ear is the whole plant body. So they get this pattern of vibrations stimulating, moving the hairs on the whole plant body, that information being transduced and translated into electrochemical signaling throughout the plant body, right? So that happens throughout the plant body itself. So we need to make an effort to truly put ourselves in their shoes. And say we can scale up, we can do some scaffolding in terms of what is it that we do. First, of course, we need to substitute one sensory for another. Because, we do things maybe with vision, we need to think, hey, how could they be doing it? So, we have many examples of sensory substitution devices. You go from optic flow, how the image expands in your retina as I'm approaching you, that the image is expanding in your retina. You might substitute optic flow for haptic flow. So we can put a gadget on your tummy and see how that expands, like vibrations on your tummy. How this is expanding as I approach you. That substitutes optic flow, right? So we can have sensory substitution devices. We know those, but we want to think how to perform those substitution devices with plant inspiration. So you may want to expand, not simply substitute, but expand your sensory capacities. For example, beyond the visible light spectrum, right? UV light, as pollinators do, right? So certainly when you have a flower with stripes under UV light, those evolve to help the pollinator land on the petal. We don't get to see it, only the pollinator does. So can we sensory expand our capacities to empathize with them? And of course, we can not just expand into something we already have beyond the visible light spectrum onto the non-visible light spectrum, but we can add modalities that are lacking as of today. So if you are doing all that, if you are thinking of robots inspired in that way, controlled in a generative fashion, think, by the way, of these root tips I was telling you as a collective agent, as a flock of roots. Think of them playing this game of being blindfolded and trying to find the treasure. So they will be all saying cold, cold, hot, hot, but collectively. So it becomes a dance. They are collectively gathering information that only makes sense from the point of view of the swarm as such, right? So that's the sort of thing I want you to think of. If we have 2 minutes left, I would love to show you something, because we've talked mostly about intelligence, cognition, but not that much about sentience itself. And the emergence of sentience is so important here. Look, I'm going to show you, do you know Mimosa pudica? Are you familiar with Mimosa? You don't need to time-lapse those guys, right? They are so fast. You touch it and they fold their leaves, right? So look at the top one. It's just the standard reaction of Mimosa. You touch it, it will fold. Now, what happens when you anesthetize a plant? When you anesthetize a plant, no spoiler, like Planta Sapiens, the book starts with this. We got to this audience, this theater, and anesthetized a plant live, right? So we put it under a glass bell, added a cotton pad, with anesthetics from animal veterinary hospitals. So the same anesthetics you use for dogs, for cats, for pets, right? The same one, isoflurane. Then the plant will suck it up through the leaves, and it will get anesthetized, right? So this is what happens down left. When you anesthetize it, look, it simply doesn't respond. Okay? Knocked off. Now, what was that? Well, you see, this is the part that plant physiology explains. I mean, isoflurane, the active principle, messes up membrane properties. So we are obsessed with neurons. We are anthropocentric, animal-centric, locomotion-centric, neurocentric. And we think that it has to do with neurons. No, it has to do with sensitivity by cells, being neuronal or non-neuronal. So the isoflurane messes up membrane properties, means it doesn't allow ions to cross the border, the membrane. So the cell effectively doesn't spike. So the action potential in neurons, you know, when a neuron fires an action potential, it depolarizes, then repolarizes, then hyperpolarizes. So that threefold phase, electrophysiological threefold phase, is a neuron firing, right? So a neuron fires this way. But plant cells fire this way too. It's the very same thing. These ions crossing the membrane. Different ions, but the functional principle remains the same. It's the threefold phase. It depolarizes, repolarizes, hyperpolarizes. That's an action potential. So plants fire spikes of voltage, and we prevent those from firing because we are messing up with those membrane properties. Ions cannot cross the membrane, right? So up until now, the story I gave you is pretty consistent with what a plant electrophysiologist could tell you, right? But what happens when you come out of anesthesia? Now, you start to fold, but you're sort of like, you know, dazed and confused. You're coming out of anesthesia. So I invite you to think, really, what does it mean to come out of anesthesia? So you human animals, you've been in a surgical room, some of you, I guess, under general anesthetics, and when you come out of anesthesia, what's happening? You are recovering something that you had lost provisionally, temporarily. So that subjective sense of awareness, oh, here I am, back again, right? So that happiness that comes with, oh, I'm back, lucky me, right? So that sense of awareness, however basic it is in plants, or however different it is from the type of awareness that we humans experience, is what you recover when you come out of anesthesia. So I invite you to think in those terms. Life has to do with being aware, meaning-making, being aware of your surroundings and doing things about it. If you wanted a definition of intelligence, we have hundreds, but I can suggest that we speak of adaptive behavior, that it's not just adaptive. So sure, there is adaptive behavior, plant adaptive behavior. Plants grow and do their things and pass their genes. But this adaptive behavior that is flexible enough to change course of action, because shit can happen. It's anticipatory. So you have to foresee possibilities ahead of time. You don't want to be late. You don't want to be catching up constantly. You don't want to simply react. You want to behave proactively. And it's got to be goal-directed towards your targets. And that's intentional behavior. So tell me what form of life can afford to live catching up or reacting. From bacteria to humans, that's what we all share in the tree of life, the need to behave flexibly, anticipatorily, and in a goal-directed manner. And that's what I take to be intelligence, quite regardless of the form, the specific form that we have evolved. Thank you.